Okay. So again, the von Neumann architecture. The document describes the design architecture for an electronic digital computer with these components. Okay. The CPU, the processing unit, the processor, the processing unit. We also have here the control unit. The control unit includes an instruction register and a program counter, which interprets the instructions in memory and causes them to be executed. Ito yung control unit mo. We also have here the memory. Again, the memory where the data is being stored. No? Not only the data but the instruction as well. Okay, the memory. We also have here the arithmetic logical unit or logic unit, the ALU, capable of operating on binary data, and the input-output mechanisms, no? Or equipment operated by the control unit. So this is the idea of von Neumann computer architecture. We have the memory, we have the processor, and we have the I/O or the input-output mechanisms. Again, when you uh, when you execute data here in von Neumann architecture, isa lang ang pinagkukuhanan niyan. Okay? Yung set of instructions mo and set of data mo is manggagaling lang dito sa memory. Magkasama na. Okay? So the control unit will process the instruction. The ALU will process the binaries. And again, pagkukuhanan niya dito lang sa isa na to. So that's the architecture designed by Neumann architecture or the Princeton architecture. Okay? So magkakasama na dyan sa processor, meron kang control unit, we have the ALU. And that's yan yung laman na CPU mo, the processing unit mo, the processor mo, no? Sa loob niyan meron kang control unit, meron kang ALU. Okay? Sa memory, nandiyan yung set of instructions mo, set of data mo, and the execution of the instruction depends on the input output. Okay? So to understand more about the CPU and the von Neumann architecture, I have here a video reference, YouTube reference that you can watch. No? I think it's all right to watch this now during our topic, during our discussion. I will play this na lang. It is a 9-minute video, so please be guided as well to understand more about the von Neumann architecture. Okay, so yeah, I will mute my mic and play the second video.
Hey, we're looking at the CPU in this video, just a real introduction to it from quite a basic level. So the CPU, if you don't know, it sits on the motherboard. This is the motherboard here, this rectangle object with loads of ports on it. This is a heatsink, and this is what's sitting on top of the CPU. CPU looks a bit like this, just a pin that plugs into your motherboard. And because it's so powerful, because it produces so much heat, it needs its own dedicated fan called the heatsink to cool it down sufficiently. So this is where you'd find it actually as the hardware device on the computer, but we'll be looking at it from a more theoretical point of view in this video. So it stands for Central Processing Unit, and it's the hardware that controls the manipulation of data, it processes data, that's what it does. And it's worth pointing out that in a computer there are potentially several processors. Not only can you have multi-core CPUs, where you have kind of like several CPUs within a CPU, if that makes sense, we'll look at that a bit later. But you can also have processors and things like graphics cards and sound cards. So processor is kind of like a general term, but it is used interchangeably with CPU, just bear that in mind. But to start off, let's just break it down into three components: the ALU, the control unit, the CU, and the register unit. So firstly, the CPU isn't obviously this simplified, but firstly the ALU is actually what does the processing that actually carries out the instructions. This is the arithmetic logic unit. It's written with a / for some reason. I can't say I know why, but it is. So ALU, arithmetic logic unit, and this actually performs the operations. So it performs the arithmetic operations like addition, multiplication, division, and so on, and the logic ones like, basically evaluating something to false or true, the two Boolean values. So this is what actually does kind of the hard work, but it's overseen by the control unit, which actually coordinates the CPU. And because the CPU is kind of what is controlling the whole computer, it's what's doing all the computer's processing apart from these potential graphics card, sound card processor, which is doing a very specific task, but generally it's controlling the whole computer. You wouldn't be watching this video if the CPU wasn't working in your device. And control unit actually kind of warms up the circuitry, it decodes the instructions, it actually deals with the data transfers and so on. And the registers are small quick stores of data. You might have, say, I don't know, 32 on your CPU, and some of them are used for programmers, some are used for the fetch execute cycle, which we'll cover later. They're very quick, very small, they're actually on the chip, and they're mostly there for efficiency because it's very slow comparatively to have to keep going back and forth between memory. They're used kind of like a temporary storage on the CPU, and they're used in its operation as well. So I wanted to talk about the von Neumann architecture briefly, and this is a term for essentially what we've just looked at. It falls under this category, and all the hardware we're looking at, all the modern computers fall under this category of von Neumann architecture. And this is often a point of confusion because it's not really taught, because it's so ubiquitous, because everything essentially is based on this architecture. It means that teachers don't really explicitly say it's von Neumann architecture. People often get confused because they see this term and they're like, I've never heard of this before, and actually it's what we've learned all along. So, you know, you don't really have to know about the other architecture, the other models available. This is going back to 1945, but essentially it says that we can break our systems down into 4 components: the main memory, or just memory, which is where the registers in this kind of model would fit in, and we'll talk about memory a lot more in the hardware videos. But also we've got ALU, we've got a control unit. This is the processing unit of this theoretical system, and we've also got input-output devices. And again, this is going back to 1945, so if you can imagine the processors and the computers as a whole back then, this is very simplistic. But this does also mean, a second major characteristic of this is that the instructions that are executed are stored alongside the data in the memory. So everything is stored in the memory alongside each other in binary, as we would have talked about at another point of the course. And this concept, the fact that the data and the instructions are stored together, is the stored program concept. And again, this is often attributed to von Neumann, perhaps unfairly to the people who actually did it, because I think he was just, anyway, he was very famous. But this contrasts with another model which isn't really used in modern computers, and this would be the Harvard model. And in the Harvard model, there's basically 2 different memories, one for the instructions and one for the data, but we don't use that, so we're not going to worry about that too much. In the von Neumann model architecture, instructions are executed sequentially, and this is how it works in our computers. So one instruction at a time is fetched from the memory and passed to the CPU, and this means that even if your CPU is absolutely rapid and is very, very fast, if the connection between the memory and the CPU in this bus, in this wire, if it's very slow, you get a bottleneck, which is called a von Neumann bottleneck, and that's just an interesting feature of this architecture. I mean, I say interesting. Anyway, we have to talk about the clock briefly in this topic. It's actually very important for the whole computer, but especially for the CPU's operation. So computers have a system clock, which is actually there to provide just general timing signals. It's not specific to anything, it's just there to, in the background, provide timing signals, and it's used by the circuits, any circuit in the computer, to synchronize itself. And it's not like a clock like we're used to, it's like a metronome in music, which kind of just produces a steady rhythm, a steady pulse of voltage. This is representing 2 different voltage levels. It could be on and off, it could be 5 volts and 10 volts, but the fact remains that it's a very steady kind of pulse. And first of all, you can use it to synchronize your circuits. So, for example, you might only transfer data on a rising edge of the clock, or you might only do it on a falling edge of the clock. You might only write data when the clock is high, asserted high, or if it's asserted low. Essentially, the devices can use the clock as they wish. And the system clock actually sits on the motherboard. And like I say, it's used by any devices, but the CPU uses it. And CPUs are designed and manufactured to operate at a specific frequency. The CPU is much faster than all the other components, so it needs to essentially have a clock that oscillates faster, that has a higher frequency. And so the CPU takes the system clock and changes it so that it's a lot faster. And this is the clock speed. And the clock speed is very important because the CPU needs a certain amount of clock cycles, or ticks, essentially an arbitrary amount of these. We could just say 1, for example, per instruction. So it uses a cycle, and this cycle is the fetch execute cycle. So all this does is this is just the process of the CPU executing a single instruction. So if we just go back a second, it might execute an instruction whenever the clock is high. So instruction here, instruction here, instruction here, and so on. And the faster this is done, then the faster the CPU will operate because it's got a higher clock speed. Anyway, so the fetch execute cycle. First of all, as we've talked about, the memory is external to the CPU and the instructions are stored in the memory. So they need to be retrieved by the CPU from the memory. And this is just the fetch stage of this cycle. So first of all, instructions go to the CPU. When they're there, they go into the control unit and the instruction is broken down into its kind of constituent parts. And an instruction is split up into its operator and its operand. The operator is telling you what it's doing, like add in this example. Actually, the addition here is an operator. And operand is another word for data. And so we have two operands here. These are two registers. So this instruction in assembly code is saying we want to add the contents of R5, register 5, to the contents of register 1. And so in this stage, it works out what the instruction is. Depending on what the operator is, it will essentially, it's relevant for the execute stage where the data is actually executed. Here, the CPU will use the information it's got from the decoding stage to activate the necessary circuitry in the ALU, or if it needs more data, or if it needs to transfer to or from registers like it does in this case, it will do it in the execute stage, and this is all done by the control unit. But the actual execution of the instructions, the following of the instructions, is done by the ALU, and the output of this is stored in a register, or may be stored in a register, and also any other data may be read or written to registers or main memory. So in this case, it's got to read from R5, it's got to read the contents of R5, and it's got to store this as R1. So it's got to do a bit of reading and writing in the execute stage. So this is a cycle, and as I say, it needs a certain amount of clock ticks per instruction, and so the faster the clock speed is, the more cycles it will do, because it's just going to inherently follow the cycle, and so the faster the clock speed is, the higher the frequency, the faster the CPU is.
So yeah, you were able to view or study how the CPU or the architecture works. No? Nandun na rin yung iba't ibang idea na pag-aaralan natin, especially the fetch execute cycle. Wherein you fetch instructions, the processor will decode it, and the set of instructions has been decoded and then executed. Mapag-aaralan din natin yun later on. So also, na ipakita rin naman sa inyo doon yung clock speed na tinatawag. The basic unit of time, o no, no, yeah, speed of time is hertz. No, kaya meron tayo sa mga processors natin gigahertz, diba? 2.1 gigahertz, 3 gigahertz. No? That's the speed of the processor processing different instructions in 1 second. Okay. So when you say 3.2 gigahertz, it is 3 billion 3 billion instructions per second. So that's the idea of yeah, of the video kanina. Ando din yung architecture, no? Yung mga architecture in the CPU. No, meron kang registers, meron kang input, may registers ka and output ka in processing in the processor itself. No. So that's the idea of on how uh, the von Neumann architecture works and the CPU itself. Later on, magkakaroon tayo ng iba't ibang modifications dyan sa von Neumann architecture na yan. Ano? Hindi lang siya kasi naging von Neumann lang basta. It needs to be developed, it needs to be improved. No? But again, that's the basic idea of how computer architectures are being designed and is being implemented and developed. No? So yeah, should as I've sinabi ko nga sa inyo, hindi lang siya von Neumann architecture, nagkaroon siya ng improvement galing dun sa kanya, no? And lumabas naman dito ngayon is yung Harvard architecture. Ano naman tong Harvard architecture na to? The Harvard architecture, no, separates, no, the storage for signal pathways for instructions and data. So Harvard architecture is a type of computer design that separates the storage and handling of instructions or the program and the data. This means the computer has two different memory spaces, one for instructions, one for data. It is often contrasted with the von Neumann architecture, where program instructions and data share the same memory pathways. This architecture is often used in real-time processing or low-power applications. Imagine you have two separate boxes, one for your Lego instruction booklet, and one for the Lego pieces. When you want to build something, you get the instructions from one box and the pieces from the other box. Tumingin, maghanap pa ng example dito eh. From the other box. This way, you can find what you need more quickly and easily. Okay. So let us now extract the idea about Harvard architecture. So in Harvard architecture, it just separates the storage and the signal pathways sa instruction memory, sa instructions and the data. No? So kung sa von Neumann, magkasama sa memory si instructions and sa data. Sa Harvard, magkahiwalay si instruction at si data. Magkahiwalay sila ng pathways, magkahiwalay sila ng memory, ng pinaglalagyan. Kumbaga, sabi nga dito, sa example natin, meron kang dalawang box. Box ng mga Lego and box ng mga libro, ng instructions. Okay? So, pagka kumuha ka ng instruction, kuha ka sa box. Kasi alam mo instructions yun. Kuha ka sa box na yun, kunin mo yung instructions na yun, kuha ka sa data ng mga recipes, or ng mga pyesa, or mga pieces. So, ito yung instruction ko, kuha ko ng ganito. Diba? So, in that case, mas, sabi dito, it's often contrasted with the von Neumann architecture where program instruction and data share the same memory and pathways. These architectures often used in real-time processing or low-power applications. You can find what you need more quickly and easily. Okay, so dito, kung magkaiba ka ng sources, and again, magkakasama na sila. No. Magkakaiba ng sources, pero magkakasama yung same applications. For example, instruction dito sa kabila, dito sa kabila. Mas mabilis yung paghahanap mo ng mga data and instructions. Okay? Unlike sa von Neumann, halo-halo dito. Excuse me. And at the same time, hindi lang naman dito sa idea ng Harvard architecture magkahiwalay yung memory and yung data. Pati ALU at IO magkahiwalay. Pero lahat yan pinagtatagpo lahat sa control unit. So that's Harvard architecture. Okay? Magkakahiwalay na yan, tsaka iba ng data pathway para mas mabilis yung paghahanap ng data and instructions. Okay? So that's Harvard architecture. That's the improvement implemented by Harvard, no? Using the von Neumann architecture. Okay? So, let us now compare the Harvard and Princeton architecture. When we say Princeton or the von Neumann architecture, it uses single memory for both instructions and data, okay, which can sometimes slow down processing because the computer has to switch back and forth between instructions and data. On the other hand, the Harvard architecture naman uses separate memories, which allows the computer to access instructions and data at the same time, making it faster in certain applications. Okay. So, kung von Neumann or the Princeton medyo mabagal. Bakit? Ito, computer has to switch back and forth para lang malaman yung instructions and data. Diba? Balik-balik yan. And then in fact, sa Harvard, sabay. Kuha ka ng instruction, kuha ka ng data, pa. Fuck. Ganun lang yan. Sabay yan. Kuha ka dito, kuha dito. Unlike sa memory, one at a time. Okay? So that's how you compare the Harvard and Princeton architectures. No? The Harvard, again, it has different sources of information, different memory sources. In Princeton, magkakasama na lahat yung instruction and data mo sa memory mo. Memory data. Okay? So this is how processors work. Okay? Ito na, ipakita na ito kayo na sa inyo sa may video ng CPU. No? The fetch, the decode, and execute. The fetch, execute cycle. When we say fetch, from the word itself, fetch, the CPU retrieves an instruction from the computer's memory. Kumukuha lang siya ng instruction. Pag nakuha na ng CPU yung address ng next instruction, it fetches the instruction from memory and brings it to the CPU. Pag nakuha niya na yung address, nakuha niya na yung instruction, bato na siya ngayon sa CPU. Ganun lang yun. Kuha lang siya ng instruction, kuha lang siya ng data. Okay? Pag nakuha niya na yon, bato ay processing unit. Anong ginagawa ni processing unit? It figures out the instructions. No? Kung ano ba ang dapat mangyari, ano bang dapat gawin. The fetch instruction is interpreted by the CPU's control unit. The control unit determines what action is required, such as adding numbers, moving data, or jumping to another instruction. Again, pagkakuha mo ng data, pagkakuha mo ng instructions, bato ay processing unit. Sa processing unit, dadalhin to kay control unit. And ang gagawin ni control unit, iintindihin niya. Ano ba to? No? Ano ba itong binigay mo sa aking instructions and data? I-decode niya, okay. Ang gagawin pala dito is i-add yung number na to sa ganitong address or itong data na to, i-move ko pala sa ganitong address or tatanong ako sa ibang instruction. Depende kung anong instruction ang meron sa na-decode na data or information or instruction. Okay? So pagkakuha ng instruction and data, i-decode to ni control unit, then bato ngayon ito sa PC, sa processing unit itself. Again, the CPU performs the action required by the decoded instruction. The CPU, maaraw na. The CPU carries out the instruction using its arithmetic logic unit for calculations or moving data between registers of memory. The result of the execution is stored back in memory or register, and the cycle repeats for the next instruction. So pagka nalaman na-decode na kung ano yung mga gagawin, i-execute na ngayon yan ni CPU. Dadalhin niya yan sa ALU para malaman kung anong gagawin. Either, ito nga, dadalhin sa ALU, the logic unit, i-move niya ba ito sa registers, i-add niya ba yung mga numbers, yung data, or ililipat niya o lipat siya sa ibang instructions. No? So after mo ma-execute yung data dito, after mo ma-execute yung instruction, repeat lang. No? Repeat cycle for the next instruction. So that's the processor's operation. Fetch, decode, execute. Fetch, decode, execute. So yun lang yun. Again, if your CPU or the processing unit mo is 3 gigahertz. So 3 billion times sa isang segundo mag-process ng operation sa CPU. So that's the idea there. Okay? So again, to further understand what fetch, decode, execute is, I have also, again, nag-research din naman ako for us to understand what fetch execute cycle is and the classifications of computer architecture. Again, kanina nakita natin yung Harvard and Princeton. And to, mas intindihan pa natin kung ano itong mga to. Okay? So let us watch the third video, okay?
Every modern computer, when you get right down to the bare metal, is doing basically the same sort of thing. I've said before that computers are just overgrown calculators, but how do you go from a simple calculator to playing video games or sending stuff over the internet or even decompressing and displaying the millions of pixels in this video? In short, what's your computer actually doing? Behind me is a scaled up version of a computer, but we're going to go much, much simpler. If you take apart your phone or PC, somewhere in the heart of it will be a central processing unit, or CPU, connected to all the other devices that make it work. Now, to show a really basic example, we're not going to use all those devices. The first one we are going to use is the clock. With every tick of the clock, our CPU goes through a step in what's called the fetch execute cycle, or fetch, decode, execute. This clock is slightly magic in that it ticks every time I click my fingers. In the CPU, I'm going to have 3 registers. These are bits of fast storage where the CPU holds values that it's working on right now. These are a register that keeps track of our instruction cycle, another that loads our instructions from memory, and an accumulator. The final thing we need in our simplified computer is somewhere to keep the instructions and any values that we end up calculating. That is RAM, random access memory, and we call it random access because it doesn't matter when or in what order the information is read or written. So, that is our computer. Let's run a simple program. All it's going to do is count up. The processor has 3 steps, fetch, decode, execute. It will just repeat those on a loop. That's the one thing that's actually built into it. So we need some instructions, actually in memory. So let's load our program into RAM. That RAM is also used to store our answers, our outputs. In the real world, these would all be stored in binary, but let's not overcomplicate things right now. Let's keep them human readable. An instruction has 2 parts. The first part is the instruction itself, and the second part is usually a memory address. On each clock tick, the CPU will do one of 3 things. It will fetch an instruction from a memory address. It will decode that instruction, and it will execute that instruction, round and round in a loop. So it's going to count up. We're going to begin with a number and add 1 to it over and over again. Fetch. 1 clock tick. The program counter is set to 0, so the CPU fetches the instruction at address 0 in the memory and puts it into the instruction register. Decode. The CPU decodes the instruction. The first part is the instruction and the second part is a location. In our case, the instruction is load and the address is 6, so we will be loading the value in address 6 into the accumulator. Execute. The CPU executes this instruction. It takes the value at address 6 and loads it into the accumulator. In this case, the value is 1. Fetch. The program counter is incremented. The CPU fetches the next instruction in the next bit of the memory. Decode. The CPU decodes the instruction. This time it's add, and the address is 7, so we'll be adding what's at address 7 into what is already in the accumulator. Execute. The CPU executes the instruction. We add the value at address 7, and in this case it's the value 1. 1 plus 1 is 2. Fetch. From the next memory location, number 2. Decode. An instruction to store the value in the accumulator into RAM at address 6. Execute. Now notice that we are overwriting what's already there, so address 6 now has 2 in it instead of 1. Fetch. A new instruction. Jump. With a jump, the next address we fetch from is the one in this instruction. Decode. So we're going to jump to address number 1. Execute. The program counter is now back at 1. The ability to jump, to loop, and to build instructions recursively is one of the foundations of computer science. So, we're back up there. Fetch from location 1. Decode. It's the add instruction again. Execute. Our accumulator still contains the values from before, so 2 plus 1 is 3. Fetch. Decode. Store again. Execute. Storing it into location number 6. Fetch. Decode. Execute, and we jump again. Fetch. Decode. Execute. Fetch. Decode. Execute. We're in a loop, and we're counting upwards by 1 on every 6th clock cycle. Our program, with these simple instructions, doesn't have a halt command or any way to interrupt it, so it will just keep incrementing that value by 1 until the number becomes so large it can no longer be held by the memory address. How it breaks then? Well, That's a whole other video, and my fingers are tired. This is a very fiddly way to program a computer. In theory, it can be done, but at this level, these instructions are just encoded in raw binary data, which is basically unreadable for humans. So we can convert that base 2 binary to base 16 hexadecimal. At that level, we call it machine code. The next step up from that is a symbolic language called assembly, which is a bit more readable, but it's still close to working at that bare metal. The original Prince of Persia game was completely programmed in assembly. That is almost unbelievable to me, painstakingly figuring out each pixel of animation and encoding it into something that the computer almost understands directly. Programming like that is complex and hard and prone to the sort of human error that introduces massive security problems. It is difficult to code and difficult to debug. So rather than dealing with the messiness or, well, the pristine logic of machine code, higher level languages were developed as an intermediary step. Those languages handle all of that memory reading and writing for us, so all we need to focus on is what we actually want the computer to do. So here's my code. Just the same instructions, phrased a little bit differently, phrased for humans to be able to read. I specify a variable, x. I then write a function that loops forever, and in each passing through that loop, we increment x by 1. Once I've written that code, I then pass it to a compiler, which turns it into that original machine code for me. So when I run the program, it's loaded into the computer's memory and executed. If I want to run it on a completely different type of computer, a Mac instead of a PC, I can compile it for that CPU instead. But this still doesn't answer the question of how the computer is doing something as complex as decompressing and displaying this video. The answer to that is speed. At the speed I was clicking at the end there, we were executing one instruction every couple of seconds on one thread, one bit of the system. A modern CPU executes billions of instructions per second, gigahertz, on multiple threads. But at the heart of your PC or your phone, there is still just a ticking clock